morning everyone. Today in this video we are going to learn about interference, basic introduction of interference, which consists of constructive, destructive interference, what are coherent sources. Two independent sources cannot produce coherent sources. Then the conditions for sustained interference pattern, and at the last, Stokes' law of reflection. So if we start with the introduction part, normally if we talk about interference, then interference tells us about the wave nature of electromagnetic radiation, that is light. We say that electromagnetic radiation, that is light, it behaves as a wave and it behaves as a particle. Both the nature of light cannot be observed in the same experiment. So interference, diffraction, polarization tells us about wave nature of light, whereas photoelectric effect, Compton effect, black body radiations tells us about particle nature of light. So today we are going to learn about wave nature of light through interference. So the phenomena of interference of light tells us about the wave nature of light in the context of light, which is an electromagnetic wave. We say that when the light from two different sources moves in the same direction, then these light waves superimpose upon each other. And according to the principle of superposition, this phenomena we call it as interference of light. Interference is divided into two parts. One we call it as constructive interference pattern and another we call it as destructive interference pattern. So in order to have constructive and destructive interference pattern, in the diagram, if we see here, that is the diagram A, which explains about destructive interference. From two coherent sources, two waves, they are traveling in the same direction, and when they are traveling in the same direction, we see that both the waves having the same frequency, but when they meet at the exit last point, we observe that one wave crest meets the trough of another wave. So in this way, the crest meets the trough of other wave, so the resultant amplitude of the wave is very less in comparison to the sum of intensities due to individual wave. So at that particular point, we observe the intensity is very less because intensity is directly proportional to the square of amplitude. And in destructive interference pattern, the amplitude is 0 over there because the crest and trough cancels out. Crest and trough meets together, so the amplitude is minimum over there, and therefore the intensity is very less, which give rise to a destructive interference pattern. On the other hand, in the diagram B, we see that at the last point, the crest and crest of both the waves meet together in such a way that the resultant intensity is greater than sum of intensities due to individual wave. So when the waves interfere in such a way, then it gives rise to a constructive interference pattern. Next is basic definition. What are coherent sources? So sources are said to be coherent if they emit waves of same frequency or same wavelength having the same amplitude, and in turn they maintain a constant phase difference between them, then such waves are said to be coherent. Constant phase difference means that either they should have a phase difference, but that phase difference should remain same at all the points when the wave is traveling, or they should have a 0-degree phase difference. Then we see that if we consider two independent light sources, then two independent light sources cannot produce coherent beam. The reason behind is that actually a beam of light is built up of waves radiated from millions of excited atoms or molecules whose vibrations are completely independent of each other, so that the initial phase of beam is absolutely governed by chance. After a time interval of 10 to the power minus 8 seconds, this phase will be randomly changed because of the fact that the excited atoms which are responsible for vibrations are replaced by other excited atoms. Thus, every source undergoes haphazard changes of phase in every billionth of a second. Hence, the resultant intensity on the screen vary rapidly with time, and that's why we say that two incoherent sources cannot produce any stationary interference pattern. Now, basic definition, what we call it as phase difference and path difference, and the relation between phase and path difference. We normally define the phase difference in terms of phi and path difference in terms of delta. So, phase difference is used to describe the difference in degrees or radians when two or more waves reach at their maximum or zero values. Same way, the path difference when the two waves crest are traveling a different distance from their sources, and when they meet at a point in such a way that a crest meets a crest, so the difference in distance traveled by these two waves is known as the path difference. So the relation between phase and path difference is that phi is equal to 2 pi by lambda into delta, where delta is path difference and phi is your phase difference. So using the same equation, we can define the path difference also. Path difference is equal to lambda upon 2 pi into phase difference. Because if the path difference between the two waves is equal to wavelength lambda, then the corresponding phase difference between the two waves is given by 2 pi. Now, further, the interference are also divided depending on the formation of coherent sources. And on the formation of coherent sources, the interference are divided in two parts. One is division of wavefront and another is division of amplitude. Division of wavefront, you all would have read in the Young's double slit experiment. What we basically see in Young's double slit experiment, a source which is a monochromatic source, and in the path of monochromatic source, we place two slits over there. Then whatever the wavefronts arising from the monochromatic source are further divided into two parts, that is by placing the slits in the path of the beam. Then the original wavefronts are divided by the two slits, and this we call it as division of wavefront. And the wavefront are also divided by using mirrors, biprism or lenses. More examples of division of wavefronts are Fresnel biprism, Fresnel mirror, Lloyd's mirror, etc. On the other hand, division of amplitude. In this method, the incident wave is divided into two parts, either by reflection or by refraction. So in this way, the beams travel different paths and finally brought together to produce interference. And division of amplitude phenomena we normally see in Newton's experiment, interference in thin films of uniform and non-uniform thickness, and Michelson interferometer. All these are examples of division of amplitude which we are going to study in the near future topics. Now, in order to have a sustained interference pattern, what are the basic conditions which should be fulfilled? The first and foremost condition is that the two interfering waves should be coherent. That is, the phase difference between them must remain constant with time. The sources should emit waves of same frequency, and the waves from the two sources should propagate along the same direction with equal speeds. The amplitudes of two interfering waves must be equal or nearly equal. Second, the separation between the two coherent sources should be as small as possible in order to have a very good interference pattern on the screen. And the last one, the distance between the source and the screen should be large as possible. So these are some conditions which must be fulfilled in order to have a sustained interference pattern. And at the last, we have a law, that is the Stokes law of reflection, which we are normally going to apply while studying the near future topics. Now, what is Stokes law? If we see the Stokes law and the diagram in this slide, we see that here N1 and N2 are two mediums. N1 acts as a rarer medium and N2 acts as a denser medium. So Stokes law states that when an incident wave is traveling from a rarer medium, and when that wave strikes on the surface of denser medium, when that wave strikes on the surface of denser medium, we see that partially the wave is reflected and partially the wave is refracted. So partially it is reflected and partially it is refracted. So when it is getting reflected, diagrammatically we can see that the phase of the wave is inverted during the reflection. Whereas when it is getting refracted into the medium, that is N2 denser medium, the phase is not getting inverted and it is moving as it is. And at the last, it strikes on the lower surface of the denser medium. There also we see that the wave is not inverting its phase and it is traveling smoothly and it is moving outward. So in this whole process, if we see here, then clearly it is seen that the phase of the wave is only changing at the point of reflection, whereas the phase is not modified at the refracted part and the reflected part from the lower surface of the denser medium. So Stokes law is applied at that place or at that point where the wave is getting reflected from the surface of denser medium. So in this diagram, there is only one point where the phase is getting changed, that is at this point, because at this point the wave is reflected from the denser medium surface and we see the change in the phase over there. So the important conclusion of Stokes law is that when a wave of light is reflected at the surface of denser medium, it always suffers a phase change of pi or a path change of lambda by 2. However, no such change in phase or path is observed when the wave is reflected at the surface of denser medium, that is the lowermost point of the denser medium surface. There we don't observe any change in the phase. So this is your Stokes law. And thank you.